Bismillahirrahmanirrahim. Assalamualaikum and good day. In this video, I'm going to demonstrate how we can analyze data by using Jenkins method by using Minitab. Before this, let's recall the flowchart of Jenkins modeling. Okay, the first step is we plot the time series and then we check the stationarity of the data in terms of the variance and then in terms of its mean, and then we identify the tentative models, and then from that we check whether the parameter of the model is significant, and then we check the residual of the model, is it uncorrelated. If all is fulfilled, then we can proceed with the forecast. If not, we need to modify the model or the parameter in the model, so then this will be repeated. So we are going to follow this flowchart by using Minitab. Let's take this data as example. Okay, the first step, we plot the time series. Okay, this is the data. So we can see that here it has trend and then the variance is increasing. So it is not constant in variance and also in mean, since if we move the frame or the date, the mean will be increasing, same as the variance, it will increasing, so it is not constant. So that is what we can identify from the plot of the time series. So let's check by using the box plots. Okay, this is how we check the variance. Okay, so this is the output for box plot. So we can check whether the lower and upper bound of the lambda estimated include the value of 1. So here it is 0.48 and 0.58, means that 1 is not included in the interval, and then the rounded value is for the lambda is 0.5. So this should suggest that the variance is not constant, so it is consistent from what we can interpret from the time series plot previously. Okay, so this how we can define what kind of transformation is appropriate for this data. So we take the rounded value of lambda here, it is 0.5, so we use it to transform the data by using the power transformation, means that we need to square root the data. So go to calculator and then put here as yt square root and then square root, include the series. Okay, so this is the data that we have transformed by using square root. So let's check back the time series plot, what happened to the data. So take this data. Okay, so this is the data after square root transformation. We can see that previously the data is not constant in terms of variance, so now we can see that it is constant. There is no more increasing variance according to time, but the trend is still existing, means that the mean still not stationary. Let's check the stationarity of the mean by using the ACF plot. Okay, we take the square root data just now. Okay, this is the ACF plot. Okay, from here we can see that it is obviously not stationary because the ACF plot dies down very slowly. So means that there are strong correlation, so it is not stationary and it has trend. In order to make the mean stationary, we do the differencing. Okay, from this we take time series and then difference. So take the square root data just now and then we put here as D1. Instead we square root and then we differentiate one time at non-seasonal lag. Okay, so this is the series after differencing. Okay, let's check what happened to the data by using the time series plot. Okay, so we can see that here there is no longer trend. So the mean seems stationary now, because whenever we look at the data, the mean is the same, quite similar. Means that we can put here in the middle as the mean. There is straight line here as the mean of the data. So we can proceed with the next step, which is the model identification. So we identify the model by using the ACF and PACF plot. Okay, take the square root and differencing data just now, and okay, this is the ACF. Okay, and then the ACF. Okay, let's recall on the guideline how we can identify the Jenkins model by using the ACF and PACF plot. So from here we know that we need to look at the ACF and PACF simultaneously. Means that we interpret them together and then we identify the model. So this is the ACF and the PACF plot of the data. So okay, let's look at the ACF first. Okay, this is what we can interpret. From here is not really clear, so we just guess first. Maybe from here we can interpret that the ACF is cut off at lag 3. So if you are not sure, okay, like this one, okay, whether it is significant or not, you can refer to the session window. This is the output of ACF value where it gives the T value here, so we can know whether the lag is actually significant or not. So you can go to Minitab help and then okay, like this. Okay, so we can check that for the T statistic for autocorrelation and partial autocorrelation. Okay, for the first 3 lag, if the T statistic, the absolute value of the T statistic is greater than 1.25, so we can interpret or conclude that the lag is significant. And greater than 3, we take lag greater than 3, means that starting 4. So if the T value greater than 2, it is significant. So here we said that not equal to 0, means that it is significant. Here we can say that the first 3 lag is significant for ACF. Okay, so for PACF, okay, we can see here until lag 10 is still significant here because it is negative 2.52. Okay, so up to lag 10. When we refer to the PACF plot, okay, we can see that it is significant until lag 10 just now according to the T value just now. So maybe we can say that the plot is dies down. Okay, so the combination is that cut off at 3 and PACF dies down. Okay, refer to the identification here. So cut off and then dies down. So the model that we can try is MA3 because here cut off at lag 3. So MA3. If you have another interpretation in terms of the ACF, let's say you said that this is not cut off, so maybe you said that this is dies down, so both dies down, so you can try on other model. So how are we going to try? Just put in here, okay, ARIMA. So here you need to be careful. So the series we have to insert here is the series after before the differencing. Okay, and then but it is after transformation. So we take the square root data because what we have the ACF and PACF here is to identify the model by using the differencing data. But when we want to insert the the model parameter. So we use the transform data only, but the differencing we put here in the model. Okay, we put here as 1, means that because here we take 1 differencing at non-seasonal lag. Okay, so we put here 1. For example, if the differencing involve the seasonal lag, so we put here the lag here, but we will need to fit the seasonal first. Okay, so this is example where the seasonality is monthly, so it is 12. So in this case there is no seasonality, so we untick this one. So we take differencing 1 time, and then just now is the model is that we want to identify is MA3. So here is for the constant, we have option whether we want to include in the model or not. So here we just include the constant first and see whether the constant is significant or not. Okay, this is the output. Okay, so MA3, so we check all the parameters whether it is significant or not. So here we can see that all the parameters is less than 0.05. including the constant, means that we can include the constant into the model. And then we also need to check whether the residual is uncorrelated by using the aljum box. Okay, this is the result. So here we have to check whether the p-value is not significant, means that it must be greater than 0.05, means that there is no correlation in the residual. So this must be greater than 0.05. Okay, this is different from this parameter just now. Parameter need to be significant so that we can include the parameter into the model. But this one we want to check whether there is no correlation exists in the residual. So means that the p-value need to be not significant. So now it just okay, we can see here that it fulfill the parameter significant, and also the residual also not correlated. I just show you here just one model. Let's say there is several or more than one model you can try on, and then check whether it fulfill the significance of the parameter and also the residual is uncorrelated. If it fulfill both check just now, so we can compare which one model is the best based on this. Okay, this is the error. Okay, the smallest is the better. So this is just for the fitted, but not necessarily the model that the best in fitted will perform the best in terms of the forecast. So I suggest that if you have several models that fulfill these two conditions, so you just take the model and then try to forecast, and then you compare in terms of it forecast accuracy. So we take the model which has the most accurate in the forecast. Let's say we want to use this model to forecast, which is the last step in the Jenkins modeling. Okay, we go back to the model just now. Okay, this is the model, and then click here forecast. Let's see, we want to forecast 10 data ahead, and then we put here okay, so this is the forecast. Okay, this is in the session window. Since just now we store the forecast in the worksheet, so this is the forecast. Okay, so it is easier for us to copy the result.